So far, we have not considered any partial fractions that have irreducible quadratics, and that happens here in example 5. When that happens, instead of using undetermined coefficients, plugging in values that are zeros for the denominator, we want to equate like coefficients. So notice we don't have to do long division here. Fourth power up top, x squared gets squared, which is a fourth, and another x is a fifth power. So no long division there. However, if we write the general form of our decomposition, that is going to look like this. We will have one term associated with the x in the denominator, two terms associated with the x squared plus 1 squared. So we'll have an x squared plus 1 term, and we'll also have an x squared plus 1 squared term. Now our numerator for the x term is just a constant a. However, this is a quadratic, so our numerator is going to be bx plus c. And the same thing here, the inside's a quadratic, so we'll call this dx plus e. Now we start off the same way. We are going to multiply both sides by the LCD, which is x squared plus 1 squared. So on the left-hand side, that cancels out our whole denominator. So we're just left with x to the fourth minus x cubed plus 2x squared plus 1. On the right-hand side, we take this whole expression, multiply it times each term. So when we multiply the first term, the x's here will cancel out. We're left with a times x squared plus 1 squared. When we multiply n times the middle term, x squared plus 1, that'll cancel out one of these. So we are left with the bx plus c times x squared plus 1. And then when we multiply n times the last term, both x squared plus 1's cancel out. We've just got dx plus e times x. Now notice we only had one zero for the denominator, which was x equals 0. And so that means we've only got one value that's nice to plug in and try and find 5 unknown coefficients. So that's why we don't want to plug in values. So what next? Well, let's see here. We want to FOIL this out. So we've got a times x squared plus 1, x squared plus 1, plus bx plus c here. And then I'm going to multiply that x in. So x cubed plus x. And then here I'll multiply that x in. Dx squared plus ex. So let's go ahead and multiply here. First term's x to the fourth. So we got the a out in the front, x to the fourth. Outer term's x squared, inner term's x squared. That's 2x squared. And the last term's 1 times 1 plus 1. And FOIL in the middle. First terms, bx to the fourth. Outer terms, bx squared. Inner terms, cx cubed. This is a square. And then last terms, cx. And then on the end, we've got our dx squared, ex. So now multiply the an times each term here, ax to the fourth, plus a times 2x squared, 2a x squared, and a times 1, a. Everything else stays the same. So now we want to collect our like terms. So x to the fourth terms, we've got ax to the fourth, bx to the fourth. So if we factor that x to the fourth out, we'll have a plus b times x to the fourth. For our cubed terms, we've just got the cx cubed. For our x squared terms, 2ax squared, bx squared, and dx squared. So factor the x squared out of here, we have 2a, plus out of here we have a b left, and out of here we have a d left. For x terms, we've just got that cx, it looks like. And then numerical terms, we've got oh no, I'm sorry, this was ex. So we've got c plus e times x. So those two are like terms. And then the number on the end, a. Now that's got to equal what we started with up here, which is 1x to the fourth minus 1x cubed. So 1x to the fourth minus 1x cubed, and then 2x squared plus 2x squared, no x term, so plus 0x, and then 1 on the end, plus 1. So that means a plus b has got to equal 1. C is negative 1. 2a plus b plus d here has to equal 2. C plus e is 0, and a is 1. So we get a is 1, c is negative 1 off the bat. So we can take that a equal 1, plug it in up here. So we get 1 plus b equals 1. Bring this 1 over as a negative. B equals 0. Take c as negative 1, plug in here. Negative 1 plus e is 0. Bring the 1 over as a positive. E equals 1. And last thing we need is d. So plug in our a is 1. That's 2 times 1, 2. B is 0. Plus d has got to equal that 2 right there. So bring this 2 over as a negative. D equals 0. So a is 1. B is 0. C negative 1. D is 0. And E is 1. So let's take those back up to the top. So a over x here, a is 1. So we can break that up to 1 over x. And then bx plus c, b is 0, c is negative 1. So it's actually minus 1 over x squared plus 1. And then dx plus e on top. D is 0, e is 1. So this is just a 1 plus 1 over x squared plus 1 squared. And dx. So these are easier to integrate. Antiderivative 1 over x, that's natural log absolute x, minus antiderivative 1 over x squared plus 1, that's inverse tangent. Remember, derivative inverse tangent is 1 over 1 plus x squared. And then this one here, that one would be a little bit more work. We won't go through all the work here, but this is a trig substitution on that one. You would use x equals tan theta, because then this denominator looks like tan squared plus 1, which is secant squared, so secant to the fourth. Bring that up to the top, it's cosine to the fourth. So this last one would be integral cosine fourth theta d theta. And then we would use half angle identities to do that. So a little bit more work there, and plus c on the end. So a little bit more work. The thing I'm mainly concerned about in this example is getting our coefficients here by equating like powers, equating coefficients of like powers.